What do you actually see when a navigation camera on Mars stares into the night and catches a visitor from beyond the sun's grasp, truth, or a trick our minds are eager to complete? On an early October night in 2005, the sky above Jezero crater is thin, cold, and almost painfully still. The Perseverance rover parks its wheels. Its navigation camera, built to measure rock slopes and safe paths, tilts up for a routine sky check. It was never designed to hunt comets, to weigh mysteries, or to carry the burden of a headline. And yet in a quick sequence of short exposures, the camera records a faint razor-straight stroke of light sliding across the Martian darkness. A mark where no mark was expected, a line where the sky should be a scatter, at once ordinary and impossible. We give that impossibility a name, an interstellar object, 3i Atlas. In astronomy, interstellar is not a mood or a metaphor. It is a measurable fact. It means the path of the object is hyperbolic, an open curve that will not close around our star. It means that if you subtract the sun's pull from its motion, there's still speed left over a non-zero velocity at infinity. This is the simplest way scientists separate visitors bound to the sun from travellers passing through. Once the idea felt mostly theoretical, an exercise in celestial mechanics. Now a navigation camera on another world might be watching one in real time. The moment is intoxicating because it is so rare. We live in a solar system that feels personal and familiar, a collection of worlds we have named, mapped, and visited. But the galaxy does not move to our rhythms. Most of the material orbiting stars never comes near us. The fraction that does and is large enough to be seen is vanishingly small. That is why each candidate from interstellar space is a cultural event as much as a scientific one. It invites us to ask unreasonable questions. Is this a rock or a relic? Is that a comet's breath or something engineered? And it forces us to confront a harder question. How do you keep your sense of wonder and still do the math? Wonder without math is just a stay. Math without wonder is a report no one finishes. So here is the promise of this film. We will keep both. We will show you what is measured and what is inferred, and we will keep those two columns separate. We will resist the urge to make the picture cleaner than the data allow. When the numbers can't carry a claim, we will say so plainly. And when the numbers do carry a claim, when they limit what is possible and what is not, we will trust them even when the result disappoints our imaginations. Start with the camera. Perseverance navigates by reading textures, edges and shadows in the terrain ahead. The same optics that can resolve a pebble at a few meters will by necessity smear together vast distances when it looks upward. On Mars, the sky is not just a backdrop, it is a geometry problem. With a distant target, each pixel spans an enormous slice of space. A streak on the image can be a lot of things: the object's faint path, the camera's tiny shakes, the planet's rotation traced across a stack of frames. Your eye is brilliant at seeing straight lines and symmetry. Your eye is also brilliant at lying to you when scale dissolves. That tension between what a picture suggests and what physics permits will guide this opening chapter. Before we can ask what 3i Atlas is, we have to ask what the camera actually captured. Is the streak a body? Is it a trail of light built up from motion? Is it both braided together by our processing? To answer, we have to move slowly because speed is the first illusion. A line across a long exposure looks fast. A short line can look fast if the exposure is very short. A line that is perfectly straight can look engineered when it is only the arithmetic of time and motion written on a digital sensor. But even as we take a careful breath, the clock keeps running. The object is falling sunward, accelerating to a peak speed as it swings through its closest approach to the sun. The window to measure, compare and model is limited by orbits and light time delays. On Earth, in orbit, and now on Mars, instruments scramble to gather whatever they can. Brightness over time, hints of colour, the tiniest deviations in trajectory. We have to make decisions about what to point and when. We have to choose which hypotheses are worth eliminating first. And we have to do it with a public watching in real time, asking questions faster than data can travel. So let's draw our map for the road ahead. First, we will define what makes a visitor interstellar in the strictest sense: the shape of its path, its energy relative to the sun, and why that matters for everything that follows. Next, we will look at the image that set this story in motion and ask what the hardware and the observing conditions allowed and what they didn't. Then we will widen the lens to the network of observations that feed our understanding. The rover's quick looks, the sharp eyes in orbit, the telescopes that watched from far away long before Mars ever did. With that context, we will return to the streak itself and explain what a stacked series of short exposures can and cannot tell you about shape, speed, and structure. Along the way, we will keep encountering the same trap. When you see something long, your brain wants to draw an object. When you see something elongated in a low-light image, your brain wants to see a cylinder, a spear, a craft. That's not a moral failing, it's a biological shortcut. Human vision evolved to detect edges and motion because edges and motion meant survival. In astronomy, those shortcuts can be lethal to understanding. The data do not care what the line looks like. The data care about margins of error, about the behavior of light under time and distance, about what other instruments saw or did not see at the same moment. The antidote is not cynicism, it is patience. Patience, however, does not mean passivity. The thing in the sky is moving whether we believe in it or not. The beauty of celestial mechanics is that it frees us from our desires. An object that is bound to the sun behaves a certain way, and a visitor from another star behaves another way. The difference is as clear as the difference between a closed circle and an open curve. A hyperbolic path has no return ticket. It is the signature of a body that wandered long before our species did, shaped by encounters we will never know, and it gives us one of the few clean categories in a messy, luminous world. That category matters because it sets expectations. A comet that has circled the sun many times has learned our star's heat. Its surface will carry scars of previous passages. It will likely wake up shed gas and dust in familiar patterns, and perhaps even fragment along predictable lines. A first-time visitor from deep space is a blank. Its composition could be different. Its reaction to sunlight could be violent or muted. Its brightness might be driven by a halo of gas or by reflective dust or by the angle at which we happen to see it. The same total light can come from a small bright object or a larger darker one. That is why pictures seduce and numbers rescue. Numbers are not cold. They are humane in the most practical way, because they keep us from convincing ourselves of what we wanted to believe at the start. If you take anything from this opening chapter, let it be this. Images are the beginning of an argument, not the end. We will honour them. We will also interrogate them. We will ask what each pixel had to do to get onto the screen. We will ask how long the shutter was open, how the planet rotated under the field of view, what the camera could resolve at that distance, and whether any other instrument saw something that would force us to rewrite the caption. None of this diminishes the marvel. If anything, the marvel grows. Consider what had to be true for a navigation camera on another planet to paint a thin line of light across an artificial retina, the alignment of orbits, the scheduling of a robot to look up instead of down, the clean air, the absence of dust, the timing of the exposures, the luck of catching a traveller at just the right moment. Consider the human chain behind it, engineers who hardened the electronics for a world of dust and radiation, planners who carve minutes from tight timetables, scientists who will argue until dawn about what any of this means. When science works, it works because the discipline is shared, and because the doubt is shared too. This is not a story about a single picture. It is a story about restraint. A claim becomes real when two independent measurements corner it from different sides. A rumour becomes science when it survives contact with an instrument that has no reason to agree. The streak that stirred imaginations on Mars must answer to other eyes. It must answer to the simple question if the object were truly elongated on the scale our first glance suggests, would the highest resolution telescopes have seen it as more than a point? If they did not, then the streak is a lesson in how motion and time build illusions. For now, put yourself in the place of the first person who saw the raw frames. Imagine the reflexive surge excitement, then caution. The desire to share, then the reflex to check. Imagine the hands that aligned the frame, subtracted the background, and saw the line sharpen. Was it the object? Was it the sky sliding past? Was it the camera doing exactly what it was supposed to do for navigation, and therefore doing exactly what astronomers have to correct for? The right move is the least dramatic one. Slow down and call for other data. Other data are coming from orbit and from Earth, from instruments that cut the sky into different colours and search for the fingerprints of gas from cameras with different fields of view and different specialties. Some will strengthen the case that this is an active comet gas boiling off as sunlight rises dust grain by dust grain. Some will suggest that activity is weaker than it seems, that the object's mass is doing most of the talking, shrugging off the tiny rocket thrusts of outgassing with indifference. All will force us to sharpen our language, not just what we saw, but what we can rule out. There is one more reason to do this carefully. Our era is defined by speed. The news cycle runs faster than the cadence of observations. Algorithms bless the boldest sentence and bury the most accurate one. A film like this has to swim against that current. It has to build trust the old way by letting you see the seams. The edits in our understanding are part of the story. When a claim changes because a better measurement arrived that is not a failure, that is the system working. Over the next hour you will watch claims rise and fall as the data sharpen. If something you want to be true doesn't survive, we'll show you why. If something you didn't expect turns out to be robust, we'll show you how. So where does that leave us at the end of this first chapter? With a picture that lit a fuse, with a vocabulary that will keep us honest, with a plan to separate what we know from what we wish, and with a single stubborn question that refuses to go away if the streak is not the shape of the object, what do the numbers say it is? In the next chapter we will answer that directly. We will take the seductive length of that line and place it beside the limits of the camera that drew it. We will compare it to measurements from instruments that see far more finely, and we will show step by step how a beautiful illusion dissolves not to kill the wonder, but to clear the way for the real story, which is bigger, stranger, and far more interesting than any single frame can hold. If a long, luminous streak on a Martian skyframe looks like a manufactured cylinder, why do the numbers refuse to agree? Begin with a simple, stubborn idea. Cameras do not see objects, they sample light. A camera's sensor divides the sky into tiny squares we call pixels. Each pixel collects photons over a short time and turns that count into a value. When you point a navigation camera built to judge rocks at arm's length at something tens of millions of kilometers away, each pixel stops being a pebble-sized ruler and becomes an enormous slice of space. The same grid that can separate two stones a meter apart will at interplanetary distances smear thousands of kilometers into a single dot. You are not looking through a telescope tuned to resolve delicate shapes. You are looking through a work tool that happens for a moment to be staring at the stars. That is why the notion of scale per pixel matters. Imagine holding a postage stamp at arm's length and asking it to draw the skyline of a distant city. The stamp can sketch light and darkness bright and dim, but it cannot etch windows or edges. At the distance where an interstellar visitor appears from Mars, one pixel on that navigation sensor can subtend a footprint that easily runs into the thousands of kilometers. A bright mark 4 pixels long is not a 4-pixel long object. It is what the sensor recorded while the scene and perhaps the camera shifted during the exposure series. The geometry of the setup dictates that any apparent length measured in pixels has to be translated back through that enormous scale before you can even speculate about shape. Now, add time. Low-light targets force a trade. Short exposures keep motion blur small but starve the sensor of photons. Long exposures feed the sensor, but let the sky slide across the frame. The normal way to thread this needle is to take many short exposures and stack them. Stacking raises the signal-to-noise ratio without saturating the image, but stacking also encodes motion. The moment you combine frames, you must decide what to align on. If you align on the ground, the stars trail because Mars rotates under the sky. If you align on the background stars, any object moving with respect to those stars will paint a line. If you align on the moving object, the stars will streak. In each case, the streak is not a physical rod in space. It is the path traced by light on a sensor over time. This is where the human eye becomes both brilliant and treacherous. We are built to finish lines that are only hinted at. A straight, narrow mark with brightness concentrated along its spine looks like a solid thing. Our brains make it a thing that is useful in a forest. It is risky in astrophotography. A streak on a stacked image is the convolution of 3 realities. The instrument's point, spread, function, the motion of the scene relative to the camera during the total integration time and the way the stack was aligned and combined. Change any one of these ingredients and the same object will present a different shape. The object itself did not morph, the recipe did. Consider angular resolution, the true arbiter of shape. Angular resolution tells you the smallest separation on the sky that an instrument can distinguish as two distinct points instead of a blur. It depends on aperture size, wavelength, optical quality, and for ground-based systems, atmospheric seeing. In space or on Mars, you do not fight Earth's atmosphere, but you still live inside the limits set by the optics and the pixel scale. If an object's apparent size on the sky is smaller than the instrument's resolving power, it is unresolved. The instrument records it as a point or a barely broader smear, no matter what geometry the object has in reality. In that regime, you can measure brightness and motion, but not shape. This is the critical counterfactual to keep in mind if the luminous line were a literal cylinder, tens of thousands of kilometers long at a distance of only a few tens of millions of kilometers. It would subtend an angular size that high-resolution instruments could not ignore. Telescopes with far finer resolving power than a navigation camera would separate the object into an extended source. They would not see a star-like point, they would see a resolved, elongated body. But independent higher-resolution observations made when the object was closer and brighter than months before did not resolve such a structure. They recorded an unresolved source. That single fact collapses the giant cylinder reading. Not because we dislike dramatic stories, but because shape is not a thing you win by insistence. Shape has to clear the bar set by resolution. At this point, some viewers protest, but the line looks engineered. It looks symmetric. It looks clean. Those are observations about an image, not about the cosmos. Symmetry in a streak often tells you more about motion and alignment than about the object. A narrow, even stripe can result from smooth, continuous movement during a well-timed stack with little jitter. The camera's point spread function, the way a point of light spreads across pixels, can be nearly isotropic, so the streak's width is set by the optics, while its length is set by motion over time. Give that setup a faint moving point and enough total integration time, and you have drawn a perfect spear of light. Nothing in that spear requires a spear in space. The language of stacking can help. Think of each short exposure as a transparent sheet with a faint dot. If you lay the sheets down aligned on the stars, the dot representing the moving object will appear in a slightly different place on each sheet. When you add the sheets, the dot becomes a line whose length is proportional to how far the object moved across the sky during the total time covered by the stack. If instead you align on the object, its dot stays put and brightens, while the background stars drag into streaks. You can make both pictures from the same data. The underlying motion is the same, only your alignment choice differs. In neither case does a line prove a rod. To sharpen this, step back and ask what else the data say. Photometry. The measurement of an object's brightness gives you hints about activity. A comet's coma, the envelope of gas and dust boiling off its nucleus, can dominate the light you record, masking the size of the solid core. Spectroscopy, the measurement of light by wavelength, can tell you what gases are present and sometimes how energetically they are being released. Dynamics. The careful fit of an orbit to many position measurements over weeks and months tells you how strongly non-gravitational forces are pushing on the body. Those three lines of evidence cross-check each other. If the object were a colossal rigid structure on the scale implied by the streak's raw length in navigation pixels, the dynamics would rebel. The path through space would not fit the tiny, precise deviations that active comets exhibit when outgassing nudges them. It would look different at a level precise instruments can see. This is the place to introduce the notion of upper limits, because it is one of the most honest tools in observational science. When a high-resolution instrument fails to resolve an object, it can tell you, if this thing were larger than X, I would have seen it as extended. Since I didn't, its size must be less than X. That X depends on distance, wavelength, exposure conditions, and the instrument's resolving power. The number is not a guess. It is a limit set by physics and calibration. When independent teams set consistent upper limits, they effectively fence in the space of possible sizes, regardless of how convincing a low-resolution streak might look to the eye. The streak cannot jump that fence just because it is dramatic. Let's also talk about noise, because noise is where tidy pictures go to die. Images at the edge of detectability are a negotiation with randomness. Shot noise from the finite number of photons, red noise from the electronic subtle gradients in the background. All of these can change the apparent thickness or smoothness of a streak. Bin a few pixels together and you boost signal at the cost of resolution. Stretch the contrast and you reveal the line, but also magnify artifacts. Strip away too much background and you might carve the ends of the streak more sharply than the data justify. None of these operations are wrong, they are choices. The responsibility is to report them and to remember that processing can make features look more object-like than the raw counts warrant. The psychological dimension is worth naming openly. A straight, bright line photographed by a robot on another planet is a perfect seed for pareidolia, our tendency to see patterns and agency in randomness. It invites narrative. The responsible move is not to shame the impulse, but to domesticate it. The way you domesticate it is by asking what independent test would have to agree for this interpretation to survive. Does a finer instrument confirm the shape? Does timing the exposures differently change the appearance? Do observations at different wavelengths which probe different physical processes tell the same story? If 3 independent methods with different failure modes converge, your confidence can grow. If they do not, the most dramatic claim loses altitude, and the more boring, resilient claim takes its place. So what precisely makes the giant cylinder claim untenable? First, the angular size argument at the distance and purported physical length implied by reading the streak as a rod. The object's image would be extended for high-resolution instruments. It is not. Second, the pixel scale argument on the navigation camera, 1 pixel spans an enormous footprint. Multiplying pixel length by that footprint without correcting for motion integration, time and alignment mistakes geometry for reality. Third, the dynamical argument orbits that conspire with such a shape claim do not match the precise small non-gravitational accelerations measured over weeks. Fourth, the multi-instrument argument independent platforms with different optics do not corroborate a resolved elongated body. A chain is only as strong as its weakest link. In this case, every strong link points away from the spectacle. Notice what the counter case does not require. It does not require cynicism or blind faith or a desire to deflate. It only requires us to use the right ruler for the job. A navigation camera is a superb ruler for nearby rocks and safe travel. It can contribute to sky monitoring, especially when stacked and processed with care, but it is not the instrument you use to dictate shape claims at interplanetary distances. That is why professional practice always leans on cross-validation. You do not crown an interpretation on the basis of a single instrument, particularly one operating at the edge of its designed purpose. You ask it to nominate a hypothesis, not to confirm one. There is a secondary lesson here about how small interpretive slips become big headlines. All it takes is one unexamined assumption, equating a streak's length with an object's length, confusing an unresolved source with a resolved one, ignoring the alignment choice in stacking for a number to inflate by orders of magnitude. Multiply that mistake by enthusiasm and you have a narrative too attractive to back down from. The cure is embarrassingly simple. Write down the assumptions, quantify the uncertainties, and invite other data to vote. The easy claims evaporate under that light. The durable ones remain and get more interesting. By the end of this detour through image literacy, we have not killed wonder. We have protected it. The streak on Mars is still extraordinary, but for the right reasons. It tells us that a moving source was present in the field during a carefully timed sequence, that the processing was sensitive enough to accumulate its path, and that the geometry of motion and exposure conspired to draw a clean, elegant line. That line is a record of movement through space, not a silhouette of a machine. It is a signature written in time, not a blueprint. And the real story does not need the crutch of an impossible shape. The real story is that a visitor from beyond our sun's long reach wandered close enough to be seen from another world, and that we caught it in the act. The real story is that when we checked those first intoxicating frames against instruments built to answer different questions, some to resolve, some to measure colour, some to weigh paths through gravity, the picture simplified and matured. We lost a myth and gained a measurement. We traded the drama of a cylinder for the discipline of an unresolved point, and that discipline is what will let us say something meaningful about size, activity, and mass in the chapters to come. Which brings us to the next part of the film. If the illusion has been stripped away, what does the full observing campaign actually look like? Who is watching from the surface of Mars and from orbit around it, and how do their roles interlock? Why, at the very moments when public attention is hottest, do official updates sometimes slow or pause, and what does that pause really mean inside the tempo of science? To answer those questions, we will widen the frame beyond a single camera and follow the flow of data across platforms and time, from quick-look frames on the ground to precision passes overhead. The streak taught us how not to be fooled. Now the network of observations will show us what is really there. Why do official updates slow down at the very moment you most want answers? And what does that pause actually tell you about how science works? Begin on the ground on Mars, where the Perseverance rover does most of its living with its eyes pointed down. It maps rubble fields and tire-wide ridges, looks for safe footholds, and builds a mental model of terrain, one cautious meter at a time. But some night schedule allowing the rover looks up. It snaps quick sequences of the sky with cameras that were chosen for reliability and ruggedness, not for astronomy. Those looks are brief and opportunistic. They are also the first thread in a larger tapestry, because while the rover gathers what it can from the surface orbiters high above Mars, sweep long arcs through space and antennas on Earth prepare to catch every bit the red planet cares to send home, the surface and the sky do not speak the same visual language. A navigation camera is fluent in edges and shadows in the hard contrast of rock against dust. An orbital camera speaks in swaths and mosaics in strips of pixels stitched into maps. Each has its own habits, its own sources of error, its own cadence for getting data on the ground. That is why a single frame, no matter how seductive, cannot carry a story alone. The truth arrives when those languages agree. Picture the path of a single data packet. A camera on Mars opens its shutter for a fraction of a second. The readout is packaged by a flight computer and queued for transmission. If the rover has a line of sight to an orbiter, it may bounce the data upward, using the orbiter as a relay. Otherwise, it may wait for a direct line to Earth. The orbiter in turn must aim its own antenna toward home and time its downlink to pass through a deep space network on Earth. The planet itself rotates, so the ground station that will receive the signal needs to be awake, pointed and ready. The one-way light time between Mars and Earth ranges from minutes to tens of minutes depending on the geometry of the two planets. The first time you see an image in a press release or on a public archive, it has travelled planetary distances, hopped between machines and survived the indifference of space. The quiet intervals in between are not emptiness. They are the time it takes to move truth. Once the bits arrive on Earth, they go through a ritual that scientists have learned not to skip. The raw frames are unpacked and corrected for instrumental effects, the grain of the detector's own electronics. Tiny offsets in the baseline signal the uneven response of pixels to equal light. These are not glamorous steps. They are the washing and chopping before the meal. Calibrations remove the fingerprints of the device from the picture so that what remains is as close as possible to the sky itself. Only then can you measure brightness or position with a straight face. With calibrated frames in hand, two styles of work begin. One is quick-look analysis, where teams ask simple, urgent questions. Is the target in the field? Is it detectable? Is it brighter or dimmer than last time? Did anything break? Quick-look results steer the next observations. They decide whether it is worth spending precious minutes to try again tomorrow, or whether the object has moved out of reach. Quick look is about steering the ship. The second style is deliberative. It is where time enters the equation. Scientists align sequences of images taken over hours, days, and weeks to build a coherent record, what astronomers call a time series. They ask how the brightness has evolved, how the apparent position on the sky has shifted, whether the colour has changed in a way that hints at gas being released or dust thickening. They fit orbits to the measured positions and look for tiny departures from what gravity alone would dictate. Time series do not shout like a single dramatic frame. They accumulate. They turn anecdotes into trends. In parallel, instruments in orbit around Mars attempt their own looks, each within its strengths. A camera tuned to survey the planet's surface at high resolution can, when pointed to the sky, capture a very different kind of scene at a vastly different effective distance. Its pixels, optimized to measure meters on the ground, become coarse rulers when turned outward. A wide-field imager can cover a larger swath of sky and catch the object even if pointing is imperfect, but the price is a blurrier sample of the object itself. Spectrometers slice light by wavelength rather than by position, and can reveal what gases glow in the coma of a comet, but tell you less about precise shape. None of these instruments is wrong, each is partial. Now, add Earth to the picture. Well before Mars ever looked up telescopes on and around our planet, we're taking the measure of the visitor pinning down its path against the starfield, night after night, measuring how fast its brightness grew as it fell inward, checking if its spectrum showed the familiar fingerprints of volatile gases. Those measurements are archived cross-checked and reported to clearinghouses that exist precisely so no single team can dominate the narrative. The Minor Planet Center aggregates astrometric positions from observatories around the world. Space agencies and major surveys publish calibrated brightness measurements. When an object is as unusual as an interstellar visitor, the cadence accelerates, but the architecture remains the same. Consensus emerges not from a single voice getting louder, but from many voices agreeing within their uncertainties. This is where you meet a second community working in the same sky-devoted amateurs, whose gear and skill have over the last 2 decades moved from hobbyist to indispensable. In living rooms and backyards, on rooftops and country hills, they aim finely tuned telescopes and cooled cameras at the same coordinates professionals publish. Many can go deeper than small institutional instruments, especially if they can stack register and filter with care. They contribute astrometric positions precise enough to matter. They produce photometry that, when standardized, can join the pool. They are often the first to notice something odd in morphology, an asymmetry in the coma, or a kink in a tail, simply because there are so many of them looking so often. Their images flood social platforms long before a space agency's press office drafts a paragraph. That speed is a gift, and a trap a gift because it widens participation and coverage. A trap because social feeds are optimized for surprise, not for error. Bars. So when official channels go quiet, what should you infer? That question reveals a widespread misunderstanding about how science breathes. A lull in public-facing updates often marks not a void of evidence, but a pile of it. It takes time to integrate new frames into an existing time series, to reconcile measurements from instruments that disagree by just enough to matter, to hunt for the systematic error you fear is hiding at the bottom of your plot. Teams have internal reviews that are unkind in exactly the way you want them to be. A result must survive colleagues who know every flaw a device is prone to, who have seen yesterday's miracle turn into today's correction. That internal friction is not politics. It is quality control. There are also mundane constraints that have nothing to do with the content of the data. Spacecraft schedules are tight and negotiated months in advance. Slipping one observation to chase a transient may force a reshuffle that affects other teams. Communication windows open and close. Solar geometry occasionally conspires to make downlinks sparse or noisy. Ground stations have maintenance and weather and competing users. Even when all the pipes are open, the people who turn raw numbers into calibrated science are not interchangeable parts. They have to sleep. They have to be sure. Silence in public is often the audible part of that taking place. The pipeline from shutter to shareable is a chain, and different links are tuned to different speeds. Raw frames can appear quickly in certain archives. Preliminary products corrected for the most glaring effects come next. Validated products with full calibrations and metadata checked follow later. Scientific analysis, the step where numbers become claims, often lags by days or weeks if the question is delicate. The same event that produces a rumour in an hour might need a week to produce a number that can survive peer review. Calling that week a cover-up is like calling the proofreader of a medical label a censor. You're mistaking caution for malice. Why emphasise time series in a story like this? Because a single frame can be a lie of omission. A comet's coma can swell or thin over days. Its brightness can spike and fall as jets switch on and off. Dust can be swept by the solar wind, briefly sculpting features that look like structure, but are only weather. Without a record of how the object evolves, you can't separate a transient flourish from a durable trait. You can't tell whether the measured non-gravitational acceleration, the tiny push from escaping gas, stayed steady or changed in ways that reveal something about the nucleus. And you can't check whether different teams measuring on different nights are in fact measuring the same thing. This is also why you see phrases like preliminary, provisional, and upper limit in the careful statements scientists make. Preliminary means the number is useful enough to plan with, not strong enough to conclude with. Provisional means the result is expected to hold, but could shift once more data are folded in. An upper limit is an honest no, the instrument did not detect the effect. If it were larger than this threshold, it would have. These phrases are not ways to hide behind vagueness. They are tools to prevent you from over-promising to yourself. Against that sober machinery, social media offers immediacy and spectacle. It collapses the distance between the person who stacked a set of frames in their kitchen and the person who designed a camera on a spacecraft. It rewards audacity and language that pretends the grey zones are black and white. The healthiest way to watch a story like this unfold is to let those streams play to their strengths, while you anchor your expectations to the slower, more boring rhythm of formal releases. Enjoy the chase. Withhold judgment until the instruments that disagree have been forced to argue. If you're looking for a simple rule, weight the claims that survive across platforms. When a brightness trend seen from the ground is echoed by an instrument in orbit around Mars, when a motion measured in a stacked rover image aligns with the motion computed from Earth-based astrometry, when a spectroscopic hint of gas shows up at the same time, another team reports morphological changes in the coma, you're watching the shape of truth appear. Instruments have different biases. Agreement is rare for the wrong reason and common for the right one. It is tempting to frame the lull in official updates as an adversarial move, us versus them, curious minds versus gatekeepers. That is theatrics. The teams behind these machines are not withholding wonder. They are trying to make sure the wonder you feel is attached to something that will still be true next week. They are also human. They know how quickly a strong statement can cement into a headline that will follow the mission for years. The decision to wait a few days to let the new frames be processed properly and folded into the time series is not fear. It is respect for the audience you are part of. There is a final reason to value the deliberate pace it makes discovery portable. An analysis that rests on a quick stack and a charismatic image is hard to reproduce. An analysis that rests on calibrated frames, documented procedures, and a time series anyone can download and fit will survive the memory of this season's drama. It can be tested by people who never saw the original excitement. It can be built upon. That is how a moment becomes a paper, and how a paper becomes a paragraph in a book that outlives us. Now pull the threads together. On Mars, a rover glances at the sky between its earthly chores. Over Mars, instruments sweep, sometimes catching a target that is effectively at infinity rather than on the ground they were built to map. Around Earth, a network of telescopes records positions and brightness night after night. In homes and smaller observatories, patient hands stack frames and measure light. Between them flows a river of bits that must be cleaned, aligned, and questioned before it can be trusted. The moments of silence are the pools where that water slows and clears. With that rhythm in mind, we can return to the simple, stubborn heart of the story. What precisely did the object do in the Martian sky when the cameras were open? How fast did it move in which direction? And what does the pattern of those motions tell us about its nature? We have learned why not every picture yields an instant proclamation. We have learned to read the pauses without reading intentions into them. Now in the next chapter we will shift from how knowledge travels to what the object itself has been doing, its motion written as light across the sky of another world, and the clues hidden in the angle, length and consistency of those streaks. If the streak isn't a photographic illusion, what exactly does the sequence of long exposures tell us about the object's true motion? Start with the simplest comparison you can make without any math at all, a streak against other streaks in the same frame. On Mars, as on Earth, the sky appears to rotate because the planet spins. If you leave a camera open long enough and a line on the ground background, stars will drag into short parallel trails. Their direction is set by the axis of the planet. Their length reflects nothing more than exposure time. Now place a moving object in that same field. If it shares the sky's apparent motion, if it is just another point riding the rotation, it will trail with the stars. If it has its own motion across the sky, its streak will cut that family of star trails at an angle. That angle is the first piece of evidence that you are seeing a body with a motion distinct from the turning of Mars. In the sequences we care about, that angle is consistent from frame to frame. Consistency matters. Single frames are generous to coincidence, sequences are not. When an object's streak maintains the same orientation relative to the star trails across a chain of images, you can be confident you are tracking a coherent path. Small variations caused by pointing jitter or slight differences in how the frames are aligned wash out when the trend survives. What remains is motion you can attribute to the object itself projected on the sky. Once you trust that the streak is real and not an artifact of stacking or alignment, you can let time into the argument. Each frame in a stack has a timestamp. The total duration of a sequence is known. The angular length of the object's streak, how far it moves across the sensor during that time divided by the duration, gives you an apparent angular speed. This is not yet a distance per second, it is an angle per second. But as a diagnostic it is powerful. It distinguishes a satellite whizzing across the Martian sky from a slow-moving background object, and it tells you whether you are dealing with a visitor whose projected motion is brisk enough to be seen in minutes, not hours. Apparent speed is only half the story. The vector matters too, the direction the streak points. Draw a line from the object's midpoint toward the sun's projected position on the sky. Draw another along the streak. The separation between those two lines helps you pass what you are seeing. For an active comet, dust and gas leave the nucleus and are shaped by radiation pressure and the solar wind. Classic dust tails tend to lag behind the orbit, while ion tails made of charged particles are pushed more directly away from the sun. If the streak you measure is the object's motion rather than a tail, its orientation will reflect the path of the nucleus across the star field, not a plume of material being pushed downwind. In the sequences under discussion, the streak behaves like motion short, steady, clean, rather than like a tail, which would be broader, often kinked and tuned to the sun's position on the sky. That observation dovetails with the object's visual character in these frames, not a dramatic sword-like tail carving the sky, but a diffuse envelope, what comet observers call a coma, that softens the point of light without resolving into structure. A coma is the atmosphere a comet makes for itself. As sunlight warms the nucleus, ices turn directly to gas and drag dust grains away. Seen from afar, that cloud can outshine the solid core by a wide margin. It blurs the object, increases its apparent size, and can trick the untrained eye into equating brightness with bulk. But a coma is weather, not architecture. The sequences from Mars show something that reads as weather, a gentle glow around a moving point rather than a geometrically crisp extension. At this point we can step carefully into the difference between apparent and true velocity. The streak gives you an angular speed on the sky, so many arc seconds per minute. To turn that into a physical speed, you need distance. Distance is not measured by the rover. It is inferred from the object's orbit, which is determined by many independent position measurements from Earth and from space. With the orbit in hand, you know where the object is relative to Mars at the time of each exposure. Multiply angular speed by distance and you have a projected linear speed across the line of sight. That still isn't the full three-dimensional velocity. Some of the motion is toward or away from the observer and leaves no trace on the sky, but it is enough to test for plausibility. A visitor on a hyperbolic path falling sunward will have a true speed that rises toward perihelion. If the projected speedy you derive from the streak length moves in step with that expectation across the sequence, dates you are reading the sky correctly. With that scaffolding in place, it is fair to ask, what does the object do over multiple nights? The most honest answer is that it moves as a single body should, smoothly, predictably, and that its brightness and appearance change in ways that look like coma behavior rather than structural change. There are no abrupt jumps in path that would hint at fragmentation. There are no sudden twists in orientation that would mark a tumbling rod seen end on one night and broadside the next. Instead, the time series suggests a nucleus wrapped in a halo of gas and dust, tracing a path that matches the computed ephemeris within the uncertainties you expect when you push a navigation camera into astronomical duty. Space weather adds texture to this picture. The solar wind, a stream of charged particles flowing outward from the sun, does not blow steadily like an ideal fan. It comes in gusts and waves. When a coronal mass ejection throws a magnetic cloud into interplanetary space comets, notice. Ion tails kink, detach, and regrow. Comae brighten or thin as charging conditions change. The sequences near the event window show hints you would expect under such weather, modest changes in the halo's extent and smoothness, but not the cataclysm that a casual reader of headlines might anticipate. That distinction matters. Space weather can sculpt the atmosphere of a comet dramatically without touching the solidity of its core. The nucleus keeps going. The painting around it shifts. Much of this argument rests on reading star trails correctly, so let's be explicit about what they are and what they are not. A star trail in a rover-aligned stack is simply the projection of Mars's rotation onto the sky during the total integration time. Its direction is determined by latitude and the camera's pointing. Its length scales with how long you added the frames together. If you reset your alignment and stack on the stars instead, the trails vanish and the stars become points. In that stack, the moving object will do the trailing. The freedom to make either picture from the same data is not a paradox. It is a reminder that you must state what you aligned on before you draw conclusions from streaks. There is one more practical reason to love star trails in this context. They bake a clock into the image. Two trails of equal brightness and length parallel across the field tell you that your stack is internally consistent. If in the same image the object's streak keeps the same angle relative to those trails over successive stacks, you can be confident that pointing jitter or frame selection did not trick you into an artificial motion. In other words, the stars are both background and reference. They let you separate the planet's spin from the visitor's glide. The qualitative conclusions you can draw from these sequences are strong precisely because they stop where the data stop. You can say the object has a real measurable motion across the Martian sky distinct from rotation because its streak angle is not aligned with the star trails and stays consistent across frames. You can say its appearance is dominated by a coma rather than a long structural tail because the light is distributed as a soft aura around a point rather than as a narrow sun-oriented extension. You can say the time series shows evolution in the halo that looks like weather, not like a body-changing shape. You can say the projected speed inferred from streak length behaves like a visitor falling inward toward the sun. Those are meaningful statements. They're also careful ones. What can't you say yet? You cannot pin down the size of the solid nucleus from these images alone. The coma hides it too well, and the pixel scale is too coarse for shape. You cannot measure the object's spin state or pole orientation. The light curve in these data is too shallow and contaminated by the coma's glow. You cannot decide between competing models of outgassing from a single band of imaging. For that, you need spectra multi-band photometry and a longer time baseline. And you cannot from a rover's vantage point alone resolve the three-dimensional velocity vector. You need the orbit built from many nights and many sites to complete that picture. If that feels like a litany of no, read it again as a map of next. To learn about the nucleus, you lean on dynamics. Tiny cumulative departures from gravity-only motion caused by jets of gas tell you how much mass is resisting those pushes. To study spin and shape, you hunt for periodic modulations in brightness once the coma settles, or you observe in wavelengths where gas contributes less. To diagnose outgassing, you look for the spectral fingerprints of common cometary volatiles and watch how they rise and fall. And to turn apparent motion into true space motion, you merge the rover's timing with the wider net of astrometry from Earth and from orbit. It is worth pausing on why qualitative is not an insult here. In planetary science, clean qualitative statements are the backbone of robust quantitative work. They prevent you from fitting the wrong model to the right data. If you know from the sequences that the object's morphology is coma-dominated, You choose light curve techniques appropriate to diffuse sources. If you know the streak's angle is steady relative to star trails, you trust your alignment and treat the angular speed as real. If you know space weather events coincided with mild changes in the halo, you consider solar wind forcing in your interpretation of short-term variability. Each of those steps makes the later numbers honest. There is also an aesthetic truth that belongs in a film like this. Watching motion written as light across another planet's sky is a way of recovering scale. We are used to photographs lying compressing hours into a second, magnifying the faint until it feels immediate. A streak earned by time reminds you that the universe is patient. The object did not hurl itself across the field. It crept and the camera caught that creeping and added it up until your eye could see it. The discipline is to honour that process when you narrate what happened. The object did not slice the Martian night. It traversed it. Precision in language is not pedantry. It is part of telling the truth. We can end this chapter where the next one begins with the limits of light. The sequences you have just walked through are generous with clues about motion and appearance, and they are stingy with clues about size. That is not a failure of the camera. It is the nature of a comet wrapped in its own atmosphere, too far to resolve and too active to behave like a bare rock. If you want to know how big the nucleus is, how heavy, how stubborn it is under the push of its own outgassing, brightness alone will mislead you. You have to look at how the path curves under forces you can't see and at how little those forces manage to move it. That is the puzzle we take up next. We will trade the seduction of glow for the sturdiness of mechanics. We will talk about why a dim object can be massive and a bright one can be small, and why the only honest way to get from light to size is to walk through motion. In other words, to understand how large this traveller might be, we have to stop staring at how it shines and begin listening to how it is nudged. Why is inferring the size of a dim, fuzzy object as hard as measuring a light bulb through thick fog? Begin with the thing itself. A comet is not a single surface, it is the solid nucleus wrapped in an atmosphere it makes for itself. The nucleus is the rock-ice core, irregular crateroid, a few kilometres across, in many cases dark as charcoal. The atmosphere, the coma, is a halo of gas and dust lofted off the nucleus when sunlight warms it. From far away, the coma can outshine the nucleus by orders of magnitude. If you point a camera at such a target and ask, "How big is it?" the camera answers honestly but unhelpfully, "Bright." Without care, your brain will convert bright into large. That conversion is where most mistakes begin. To keep from sliding down that slope, we separate contributions. The light you detect is some sunlight reflected by dust in the coma's sunlight, reflected by the nucleus, and at certain wavelengths light emitted by gases in the coma itself. Each term scales differently with the distance, geometry, and composition. If the coma is active, its share dominates and the nucleus becomes a hidden actor. You can still learn about activity from brightness, but you cannot read size off the top of the curve. 3 levers control how bright a sunlit object looks to you, how reflective it is, how the light strikes and leaves it, and how far it is from the sun and from you. Reflectivity is the albedo, the fraction of incoming sunlight a surface sends back. Dark surfaces have low albedo. Bright ices and fresh frost can have high albedo. Geometry enters through the phase angle, the sun-object-observer angle. At small phase angles near full illumination, more of the lit side faces you. At large phase angles, you view the object more crescent and the brightness drops. Comet dust complicates this with a phase function, a curve that tells you how strongly the dust reflects or forward scatters light as the angle changes. Distance finally pulls the brightness down with an inverse square law twice over. Once for how much sunlight reaches the object and once for how the reflected light spreads out before it reaches you. Those are the rules. Now the intuition trap. Human vision is superb at turning luminance into size in everyday life, because your brain quietly assumes constant reflectivity and fixed distances. A white baseball and a white volleyball at arm's length. The volleyball looks larger because aside from size, everything else is similar. Space does not honour those assumptions. 2 objects can be at different distances with different albedos under different phase angles, and their comae can add brightness that has nothing to do with the solid body. Your eye trained by Earth will still try to do the volleyball trick and will be wrong. Make the trap concrete with a thought experiment in plain numbers. Imagine two spherical objects at the same distance, both seen at the same favourable phase angle, so geometry is not the spoiler. Object A has a high albedo of 0.6 and a radius of 5 kilometers. Object B is dark with an albedo of 0.04. For them to look equally bright in reflected sunlight, the product of albedo and cross-sectional area has to match. Since area scales with radius squared, set PA(RA2) equals PB3 RB2. Solve for RB RB2 equals PA PB RA2 is 0.6 0.04. 25 and 15 25 and 375, so RB 10 kilometers. In other words, a 10 kilometer bright body and a roughly 38 kilometer dark body can deliver the same brightness. If you only look at the light, you cannot tell which reality you are in. Now thicken the fog with a coma. Dust grains are usually brighter than a bare space-weathered nucleus. They also scatter light forward efficiently at certain phase angles, which can make a comet appear to surge in brightness when the sun-object observer geometry lines up. Gas adds its own tricks. Emissions at specific wavelengths can make narrowband images flare without any change in the nucleus. If you observe in a broadband filter that mixes dust reflection and gas emission, the coma's behaviour can mask subtle changes in the core. The net effect is that two comets with equal nuclei can look wildly different because one's coma is denser, dustier, or caught at a geometry that favours forward scatter. Apparent magnitude. The astronomer's way of reporting brightness as a single number is a useful ledger entry but a poor tape measure. To compare objects fairly, you convert apparent magnitude to absolute magnitude. How bright would this be if we moved it to a standard distance from the Sun and from the observer, and if we observed it at a standard phase angle? That normalization is straightforward for Arellus solid asteroids. For comets it is messy because the coma's contribution is coupled to the very sunlight you are trying to normalize away, and because the coma can grow and shrink on timescales shorter than your observing cadence. A single absolute magnitude value can hide a moving target. Photometry. The practice of measuring brightness does give you levers to separate pieces if you use it carefully. Aperture photometry sums the light in a chosen circle around the object. Change the aperture size and watch how the total light grows. That curve can hint at how much light is coming from a compact core versus a diffuse halo. Use an annulus just outside the aperture to sample and subtract the local background so you do not mistake sky glow for comet light. Repeat the measurements in different bands. A red filter can be more sensitive to dust reflection. A narrow band tuned to a known gas emission can trace activity. None of this yields size by itself. It yields a structured set of clues about what you are adding together when you say bright. Processing choices can also nudge you into false confidence. Stack many short exposures to lift a faint comet out of the noise and you improve your detection, but if you align on the stars, your aperture will sum light along a streak, not over a point, artificially boosting apparent brightness compared to a single short exposure. Stretch the contrast aggressively, and you bring out the coma's wings while making the central peak look sharper than the data justify. Subtract a background with the wrong scale, and you can carve away real halo light or bake in gradients that mimic structure. These are not moral failures. They're reminders that brightness is not a raw truth. It is a product of method. There is a second intuition trap that trips even careful readers of data, the belief that a smooth, unmodulated light curve means a large, slow-spinning body. In reality, a bright coma can smother rotational signatures from the nucleus. As the core turns, patches of fresh ice might come into and out of sunlight, but the coma's constant glow fills in the valleys and flattens the peaks. You can mistake no modulation seen for no modulation exists and infer a size from silence. The better reading is humbler, you are sensitivity limited by the coma. So what do you do instead of guessing from glow? You pivot from light to motion. The size of the nucleus hides in dynamics, specifically in how little the object's path deviates from what gravity alone would dictate. As gas streams off the surface, it acts like a series of tiny thrusters. The thrust depends on activity, the response depends on mass. A small, low-mass nucleus gets shoved around more by the same outgassing than a massive one does. Over weeks and months, those tiny shoves show up as non-gravitational accelerations in the orbit fit. If for a given level of observed activity the orbit barely budges, the nucleus must be hefty. If it squirms, the nucleus is probably light. That is a mass-to-thrust story, not a brightness story. Before we cross fully into mechanics in the next chapter, it helps to name a few vocabulary words in plain language so they do not hang in the air like jargon. Albedo is just reflectivity, the percentage of sunlight a surface throws back. Phase angle is the geometry of illumination, the angle between the sun and the observer as seen from the target. It tells you how full or crescent the object appears. A phase function is a recipe that converts phase angle into a brightness factor for a given kind of surface or dust. Apparent magnitude is the brightness you measure here and now with all the distances and angles nature gave you on that night. Absolute magnitude is the standardized brightness you would get if you could teleport the object to agreed upon distances and angles. And separating nucleus from coma is not a matter of willpower, it is a matter of using aperture's colors, and when you are lucky, spatial resolution to assign the right weight to each contributor. A verbal case study ties all this together. Picture two comets at the same distance from the sun and from the observer. Both present as faint fuzzy points with no obvious tail. Comet 1 has a relatively bright compact coma dominated by fine dust, a high effective reflectivity, and a small dark nucleus that contributes little to the total light. Comet 2 has a more tenuous coma and a larger, darker nucleus. In a broadband image, they can have the same apparent magnitude. If you rely on brightness alone, you might call them twins. If you switch to a narrow band that isolates a gas emission Comet 1 flares because it is actively venting, Comet 2 does not. If you measure their orbits over a month, Comet 1's path shows tiny but measurable non-gravitational accelerations. Comet 2's path hugs gravity more tightly. The first is probably smaller and more vigorously active, the second larger and more sluggish. The picture that brightness suggested two equal lights dissolves under better questions. Why does our intuition fail so reliably here? Because in human scale settings, light and size correlate tightly enough to be a shortcut. In space, those shortcuts break. Reflectivity varies wildly. Geometry changes night to night. Distance swings by tens of millions of kilometers. Comi breathe, gas glows. Everything that could keep bright from mapping cleanly to big conspires to do so. Rather than fight that, you formalize it. You write down the pieces, you measure them separately when you can, and you decline to draw a size from a number that never promised to carry one. None of this means brightness is useless. On the contrary, brightness is a vital witness, just not a lone one. Secured to a time series, it tells you how activity waxes and wanes. Measured in multiple bands, it hints at composition. Tracked alongside geometry, it lets you apply phase functions and strip away some of the fog, but the tape measure lives elsewhere. It lives in the orbit where mass answers to force. That is where we go next. Having learned to distrust size claims built on glow, we will turn to the sturdier evidence hidden in the path itself. We will look at how a comet's own exhaust nudges it, how those nudges accumulate into a measurable deviation, and how by comparing thrust to response you can bound the mass of the nucleus. In short, we will trade the seduction of apparent magnitude for the honesty of mechanics, and we will see how far that honesty can carry us toward an answer that brightness alone could never give. How much can a tiny slip from a gravity-only path tell us about the true mass of a traveller from interstellar space? Begin with the push and the shrug. Comets push themselves. As sunlight heats their surfaces, ices vaporize and escape. Gas flows off the nucleus, drags dust along, and produces a weak thrust. The nucleus shrugs back. How much it moves in response depends on how heavy it is. A light nucleus squirms, a heavy nucleus barely budges. That interplay thrust versus response is the heart of non-gravitational acceleration. Non-gravitational acceleration is just what the name says, any small departure from the trajectory you would compute if gravity were the only force. Astronomers fit orbits to repeated position measurements over days and weeks. The fit starts with gravity, mainly the sun with small corrections for planets, and then asks, whether the measured path systematically drifts from that ideal. If it does, they add a term for a tiny push, typically split into 3 directions outward from the Sun along the path of motion and perpendicular to the orbital plane. Those components are labelled and solved for like any other parameters. They are small, too small to notice in a single night, but they add up. Over time, the orbit that includes them lands closer to the truth than the one that ignores them. Where does that push come from? Physically. Imagine the nucleus as a dark, ragged lump of ice and dust. Sunlit patches warm above the local sublimation temperature. Molecules break free and stream away at speeds of hundreds of meters per second. If the venting is broadly symmetrical, the thrusts cancel and the net push is tiny. If a few active regions dominate, or if thermal lag means the hottest spot is not where you expect an imbalance appears, the imbalance is a thruster. In engineering terms, thrust is mass flow times exhaust speed. In comet terms, it is how much gas leaves per second times how fast it leaves summed over the active vents and averaged over the spin. The acceleration the nucleus feels is that thrust divided by the nucleus mass. That last division is where mass hides. Suppose independent observations photometry spectra suggest the comet is active. Gas is coming off. Dust is present. If despite that activity the best fit orbit shows only a tiny non-gravitational acceleration, you've learned something completely different from brightness. The nucleus is resisting the push. Either the activity couples weakly to the nucleus's motion, or the mass is large enough that the same thrust produces only a small acceleration. Conversely, if the fit requires a relatively large non-gravitational term while the coma looks modest, the nucleus may be small or the active vents unusually efficient at producing directional thrust. To turn this logic into a size estimate, you need 2 kinds of input. First, you need an estimate, even a crude one, of the activity level, how much mass is being lost per second, and at what effective exhaust speed. Spectroscopic detections of common volatiles combined with models of how dust contributes to brightness let you bracket that. Second, you need the orbit fit to tell you the acceleration components that best explain the positions over time. With thrust on one side and acceleration on the other, mass follows from mass equals thrust divided by acceleration. If you adopt a plausible bulk density, a range not a single number, you can translate mass into a range of diameters. Do not expect single-line answers. Every step carries uncertainty. How much gas is escaping depends on species temperature and which fraction of the surface is actually active. The exhaust speed is not a single number. Jets and diffuse flow coexist. The acceleration you infer from the orbit can be biased if the position measurements were taken from images where the coma pulled the photocenter away from the true nucleus location. And the bulk density of cometary material is a matter of range, not of precision. Each uncertainty propagates. The right way to report the result is as a bracketed estimate with assumptions stated. Even with those caveats, orders of magnitude matter, and they are your friend if the dynamic fit wants a push that is an order of magnitude smaller than you would expect for a vigorously active kilometer-scale nucleus. Then either the activity is overestimated, the coupling is inefficient, or the mass is higher than your prior. Each option can be tested. You can check the activity estimate against independent data sets and wavelengths. You can examine whether the geometry of vents and spin state would naturally cancel thrust. Or you can entertain that you're looking at a heavier than typical core, and then ask whether other lines of evidence support that view. The reverse logic also helps police speculation. Dramatic story might claim a massive elongated structure because an image looked that way. Dynamics can puncture that quickly. A truly enormous rigid body would be both dimly affected by outgassing and dimly active in the first place. If the spectra show gas and the light curve suggests a lively coma, but the orbit still shows measurable non-gravitational accelerations, you are not looking at an iron bar. You are looking at a comet doing comet things with the exact balance of thrust and mass still to be nailed down. Comparison clarifies where an interstellar visitor sits on the spectrum. Previous interstellar objects taught us 2 complementary lessons. One showed measurable non-gravitational acceleration, with no obvious gas signatures at visible wavelengths sparking debate about exotic outgassing or other mechanisms. Another looked and behaved like a textbook comet with gas and dust and dynamics to match. Place a new visitor between those cases and ask simple questions. Does the dynamical fit require non-gravitational terms at all? If so, are they aligned mostly away from the Sun as you would expect from sublimation-driven thrust, or do they point oddly? Is the magnitude of the acceleration broadly consistent with the level of activity seen, or is there a mismatch? Mismatches are where hypotheses are born, but they also have a habit of shrinking when better data arrive. The temptation at this point is to leap from heavy nucleus to extraordinary origin. Good films resist that leap because the data carry you further than the headline. A bulky nucleus is a perfectly natural possibility. Comets come in a range of sizes. An interstellar object large enough to keep its path close to gravity despite activity is not metaphysically strange. It is simply rarer in a small sample that so far includes only a few known visitors. Sampling bias, discovery thresholds, and plain luck shape that sample. Before you posit machinery, you exhaust the organic explanations. That is not small-mindedness. It is how you avoid building castles on preliminary fits. Still, a documentary owes you the other side of the ledger, the hypotheses that use tension in the data as a launching pad. What would an engineered body have to do to masquerade as a comet in dynamics? It would have to produce a thrust pattern in step with the Sun object geometry, or produce none at all and rely on gravity alone. It would have to mimic gas signatures that track temperature and distance from the Sun, or full spectrometers designed to separate reflection from emission. It would have to show surface colors and polarization consistent with dust, or invent a new way to scatter light. Every one of those tests is to its disadvantage, and that asymmetry is the point. The burden of proof is heavy because the natural hypothesis already explains the ordinary and most of the extraordinary. The honest treatment of uncertainties is not to say we don't know and stop. It is to say we don't know yet, and then list the measurements that will move the needle. Continued astrometry matters. The longer the time base, the better you can distinguish real non-gravitational terms from random astrometric noise. Observations that reduce coma-induced centroid shifts by using shorter exposures, better seeing, or higher resolution trim a subtle pernicious bias. Multiband photometry tied to absolute calibrations pins down the activity level more tightly, letting you narrow the thrust side of the equation. Spectroscopy tracks species and their production rates, connecting chemistry to dynamics. Polarimetry constrains dust properties that affect how brightness maps to mass loss. Thermal infrared measurements, when available, provide energy balance constraints that limit how much sublimation is physically plausible at a given heliocentric distance. Each dataset doesn't just help, it chops off whole branches of misunderstanding. Engineers and dynamicists also model the coupling between activity and acceleration. Vents are not neat thrusters bolted to a chassis, they are messy. As the nucleus rotates, a sunlit area may turn on peak and turn off. Gas escapes over rough topography. Dust loading changes the exhaust. Thermal inertia shifts peak activity away from local noon. Those effects smear and redirect thrust over a rotation, often reducing the net acceleration compared to naive estimates. Incorporating rotation-active area maps and plausible topography can reconcile an apparently low acceleration with a modest nucleus or vice versa. The point is not to produce the answer you want, but to inhabit the physics well enough that your residuals shrink for the right reason. Systematic error deserves its own paragraph because it is the quiet saboteur of beautiful fits. Astrometric reductions can inherit small biases from star catalogues, optical distortions or color terms that shift positions by fractions of a pixel, enough to fake or erase a weak non-gravitational signal. Photocenters drift tailward in asymmetric comae, pulling the measured position away from the true nucleus by an amount that depends on the aperture size and the seeing. Mixing data sets with different systematics without proper weighting can spin a clean physical story out of calibration mismatches. Scientists fight these by using consistent reference catalogues, modeling instrument distortions, measuring and correcting for coma asymmetry, and letting their software be skeptical outlier, resistant fits honest error flaws, and tests that ask whether removing a small subset of data changes the answer. When the dust settles, sometimes literally, you will not be left with a single number carved into granite. You'll be left with a range for mass and diameter that narrows as the campaign proceeds, anchored by a dynamical measurement that brightness cannot fake. Perhaps the range points to a nucleus a few kilometers across with a normal cometary density. Perhaps it favors the upper end of plausible sizes given the activity. Either outcome is a result, and both have consequences for how we think about the population of interstellar visitors. If the object is on the heftier side, it nudges us to reconsider discovery biases and capture probabilities. If it is modest in size but dynamically lively, it deepens the puzzle of how different surfaces and volatiles behave under a new star. To keep our promise of balance, lay the two broad interpretive tracks side by side. The natural track says we are watching an active comet on a hyperbolic path. Its gas and dust make a coma. Its outgassing produces a small thrust. That thrust, filtered through mass and rotation, shows up in the orbit as a non-gravitational term. The uncertainties lie in the details: how active, how massive, which vents, what density. The speculative track says perhaps something else is at work, unusual physics or unusual origin. It must explain at least as much data, at least as cleanly, with testable predictions that differ from the comet case. The moment those predictions fail, no gas where gas should be, no correlation with solar distance, no alignment of acceleration with expected directions, the speculative track loses altitude. If it survives new measurements, it earns another round. A last word on storytelling ethics, because dynamics encourages overreach. A single parameter that looks crisp, a non-gravitational coefficient with tidy uncertainties, invites grand inferences. Resist. That parameter is a summary of complex behavior. It is sensitive to assumptions about activity geometry and data reduction. Use it as the backbone of an argument, not as a megaphone. Say what it rules out, say what it allows, say what would change your mind. And then look ahead. The same mechanics that weighed this visitor also lets us ask a bigger, older question. If some interstellar objects carry unusually large stubborn nuclei, what role might such bodies play when they wander into young gas-rich disks around other stars? Could a solid core dropped into a nursery of dust and gas accelerate the birth of a giant planet serving as a ready-made seed, where growth would otherwise stall? That is where we go next. We will leave the ledger of forces and follow the idea into the wide arena of planet formation, where a single heavy traveller can change the odds for an entire system. What if interstellar wanderers don't just pass through but sometimes become the seeds of new worlds? A planet begins as dust. In the bright, brief youth of a star, a protoplanetary disk of gas and solids circles the newborn sun. Micron grains collide and stick into pebbles. Pebbles grow into boulders. With luck, boulders concentrate into kilometre-scale planetesimals. From there, gravity takes a larger share of the work. Clumps attract more clumps. Cross-sections inflate and cores begin to emerge. But the clock is loud. Disks do not last forever. Ultraviolet light and stellar winds strip them. Observations of young stars show that disks typically disperse within a few million years and rarely survive past 10. To make a gas giant in time, the standard core accretion picture demands that a solid core reach roughly 10 Earth masses while the gas is still there to be captured. That sprint from dust to core is where the model feels the strain. Disk physics offers help. Streaming instability can concentrate pebbles into dense filaments that collapse into planetesimals. Pebble accretion, where a modest core grows rapidly by the gobbling small solids that are slowed by gas drag, can accelerate growth once a body reaches a threshold size. But even with those boosts, certain environments look tight on time. In low metallicity disks with fewer solids in regions where drift pulls pebbles starward quickly, or around stars whose disks evaporate early, core formation races the end of the runway. Now consider a different opening move. Instead of waiting for dust to bootstrap itself into a seed, imagine an already large body wandering in from interstellar space and becoming bound to the disk. It does not need to arrive as a planet. It could be merely a giant planetesimal dozens to hundreds of kilometers across or larger. If captured, the body starts on third base. It can immediately begin sweeping up material by gravitational focusing. It can trigger local streaming instabilities and seed pressure traps. If it is large enough to enter the efficient regime of pebble accretion, its growth can go non-linear. In a disk whose clock is running down a head start of that kind could change the odds. Capture is the first question you have to clear. Free fall into a star's gravity well does not by itself make a body stay. Energy must be dissipated. In a gas-rich disk, the pathways exist. Gas drag converts relative motion into heat and can bleed enough energy to turn a passing trajectory into a bound orbit, especially if the intruder crosses dense midplane regions. Three-body interactions, encounters with a forming giant or with multiple planetesimals can also shuffle energy and trap a visitor. The deeper gravity and larger hill spheres of more massive stars increase the volume of space where such captures are possible, and the denser birth clusters of massive stars raise encounter rates. That logic lines up with an observed trend gas giants are more common around more massive stars. The match is suggestive. It is not proof. If capture is plausible, what does a seed do next? Size sets the regime. A seed below the pebble accretion threshold still helps by stirring local solids and gravitationally focusing pebble and boulder impacts. A seed above threshold interacts with gas and pebbles as a coupled system. Pebbles drift toward an end gas drag and are deflected into its hill sphere where drag robs them of energy and they settle onto the core. Growth can be fast enough to build a 10 Earth mass core within a disk lifetime in favourable conditions. As mass rises, the seed carves a partial gap, creating pressure gradients that trap more pebbles and further feed the core. The feedback is constructive, the runway extended. This is the idea often called planet seeding by interstellar objects. It is by design a hypothesis. It takes what we already know about core accretion and asks whether nature sometimes supplies the core. It offers an explanation for why gas giants should be easier to assemble around stars and in environments where capture is efficient. It promises to soften timescale problems without rewriting disk physics, but hypotheses earn their keep by making predictions you can test and by risking being wrong. What would you expect to see if seeding mattered at a non-trivial level? Start with statistics. If capture probability rises with stellar mass and with gas density, then gas giant occurrence should correlate not just with stellar mass and metallicity in the familiar ways, but show excesses in young clusters where close encounters with interstellar bodies are more likely. If seeding sometimes happens late near the end of the disk's life, you might find giants in systems where standard models predict the odds were poor given the inferred disk lifetimes. Those are population-level signals. They are noisy, but they are measurable as exoplanet catalogues grow. Composition offers a second line of attack, a captured seed formed under another star's chemistry. If it survives as the heart of a planet, it might carry isotopic or elemental fingerprints that diverge it from the disk's baseline. Those differences would need to survive later mixing and accretion, and they would be hard to measure directly in exoplanets. But in principle, for giant planets with atmospheres enriched by dissolved solids, high-precision spectroscopy could someday flag outlier ratios that are awkward to explain with local disk gradients alone. In our own system, the search would focus on subtle anomalies in meteorites and planetary interiors, always with caution because local heterogeneity can mimic foreign signatures. Disk structure is a third testbed. High-resolution images of disks show rings, gaps and vortices, the scars and wakes of planet formation in progress. A captured body on an initially inclined or eccentric orbit could carve features with geometries that differ from planets that grew quietly from the midplane. Over time, gas drag damps those excitations, but the earlier symmetries might be detectable as misaligned rings, warped shadows, or localized dust traps that switch on in step with an intruder's passage. Instruments that can monitor disks over years, not merely take snapshots, would be the tools for that job. None of these signatures are unique. That is the hard part. Core accretion without seeding can also make giants around massive stars. Disks can inherit chemical diversity from their birth clouds. Rings and warps can come from planets born in place. That is why the burden of proof is high. The seeding idea has to outperform simpler stories across multiple independent kinds of evidence. If it is real, it should leave a family resemblance across systems that cannot all be explained away by the same local effects. Clear conditions necessary and sufficient help keep the debate honest. Necessary a mechanism to capture an interstellar planetesimal at non-zero probability under plausible disk conditions. Necessary a captured seed large enough to enter or quickly reach the efficient pebble accretion regime before the disk disperses. Necessary a disk that still contains enough solids and gas to feed rapid growth when the seed arrives. Sufficient if met together, the resulting growth trajectory achieves core masses on timescales shorter than the residual disk lifetime and imprints observable structural or compositional signatures that differ from unseeded growth. Fail any one of those and seeding becomes rare decoration rather than common engine. What would falsify the idea or push it to the margins? If improved statistics show that gas giant occurrence tracks only metallicity and disk mass with no residual dependence on capture-friendly environments, the room for seeding shrinks. If detailed simulations that include realistic gas drag turbulence and three-body dynamics show capture cross-sections far too low at typical relative speeds, the mechanism becomes astrophysically negligible. If compositional surveys converge on tight relations between stellar and planetary abundances, with scatter fully explained by local processes, there is little appetite left for imported cores. A good hypothesis writes its own exit. Where does the current visitor fit into any of this carefully? An interstellar body seen in our sky is not by itself a seed, it is a messenger. It reminds us that solid bodies travel between stars in non-zero numbers, that interstellar space is not empty of building blocks, and that disks do not evolve in isolation. Whether this particular object is large or small by comet standards, whether it is a vigorous source of gas or a heavy stoic nucleus, it is proof of possibility. That is its gift to this question. There is also a human thread, and it belongs in a conclusion. Science asks for two muscles at once: skepticism and imagination. Skepticism keeps you from stapling the most exciting story to the first intriguing image. Imagination keeps you from shaving the sky down to only what you have already seen. The discipline is to let imagination propose and let skepticism dispose. The planet seed idea earns time on the stage because it solves a real timing problem and because it plugs into processes we already trust. It earns no free passes. It will stand or fall on the weight of future measurements and the stubbornness of orbit fits. So the film closes on a wide frame. A rover on Mars glances up and catches a line of light that turns into a lesson about scale motion and patience. The line leads to questions about mass and force, about how much a small push should move a heavy thing. Those questions open into older ones about where planets come from and how often chance favours their birth. Somewhere most nights a disk is cooling, pebbles drift, vortices gather dust. Maybe rarely a traveller from another sun drifts in, gives gravity something to work with and tilts the odds toward a world that would not have been. Whether or not this is how some giants begin the habit we practice here is the same. We will need to find out, respect the data, state your uncertainties, test the beautiful idea where it is most fragile, and remember that the universe does not owe us an easy story. If we keep those terms, then each interstellar visitor, however ordinary or strange, will do more than pass by. It will leave us better at asking the next question.